So now that we have sort of a working knowledge of functions, okay, we can actually start thinking and working on calculus, okay? And calculus has two goals, okay? And they both have to do with the Euclidean plane, okay? Here's the first one. So we have a function. We have some line that is tangent to our function at a point, right? Let's call our point, say, P, and our line T, okay? Tangent meaning it touches it only at one point. Calculus seeks to answer the question, okay, what is the slope of this line T? Okay, it's really interested in figuring that out, okay? The other one is, say you've got some region of the plane, right? Call it R. You have this little cell here, right? Calculus is concerned with the question of what is the area of this region R, okay? And while these seem to have almost nothing to do with each other, by the end of the quarter, we'll hopefully see that these are a little bit more connected, okay? When we're looking at the area of these regions, doing a thing called integral calculus, and looking at these tangent lines, it's called differential calculus, okay? And we're going to spend the majority of our time this quarter on differential calculus, and while looking for the slope of that line may seem pretty meaningless, we're going to see that that's actually mathematically equivalent to looking at the rate of change of that function. And rates of change are something that we are interested in, okay? How quickly is demand changing? How quickly is this particular stock increasing or decreasing in value? And then what is the rate of change of my, emotions at hearing that news? And before we can do this, okay, we need to look at something called limits, okay? And we're going to do that through an example that is vaguely related to something like this, okay? Looking at rates of change. So here's our example, okay? Say you have this new train, right? For some reason, mathematicians and physicists love models that have to do with trains, in terms of like explaining things with trains. So say you have this train, and the position of this new, crazy fast train, it's one of those ones that like works on magnets. Okay. And the position is governed by we'll say S, we'll say P, which is a function of time, right? And we'll say that that's 2 times t squared. I'm actually going to move this down here, okay? We'll give our domain down here, let's say t is between 0 and 10, okay? So we have these positions, right? We're going to know that at time 0, right, we're at, say, 0 feet, right? What about at time 1? Well, at time 1, we're going to have gone, say, 4 feet, right? So this is t equals 0, that's t equals 1. At t equals 2, well, we've gone 16 feet, right? So if we're trying to keep a scale, 4, 8, 12, 16, right? So that's 16 feet at t equals 2. At t equals 3, we're all the way up at 36. All the way up here, okay? That's t equals 3. And then, our scale is going to fall apart pretty quickly, right? And here at t equals 10, we're all the way 400 feet away from our start, okay? So my question for you is, if you looked down at your speedometer right here, right? How fast is the train going, right? Clearly it's going to be going pretty fast, and it's only getting faster, right? But how fast is it actually moving? And right away with this information, it would seem largely impossible to actually tell, right? I can look at the average, velocity, the distance traveled over the time it took, right? But as far as how fast you're going at a particular moment, we don't necessarily have the tools for that. So we can certainly approximate it, okay, by looking at, something like the average velocity between second 2 and 4, right? That will give us a decent approximation, right? So we can say there's average speed. What's going to be what? Well, it's going to be f of 4 minus f of 2 all over 4 minus 2, right? If you remember back in 118, this is the same as the average rate of change. And as we go to work this out, I realized that that should be 4t. I'm sure some of you caught that when you noticed that what I had written here didn't line up with that. I copied from my notes wrong. But with this correction, let's sort of take a look. F of 4, well, it's going to be 4 times 4 squared minus 2 times 2 squared over 4 minus 2 is 2. Evaluating those, we're going to have, it looks like 64 minus 16 over 2, which is then equal to 24 feet per second. Okay, that's our average speed between times 2 and 4. Okay, so the question is, can we do better, right? Can we find a better approximation? And one of the ways that we can do that is considering the general case, okay? And in general, the average speed between times 2, we'll just say some generic time t, right? Let's set this equal to some new function, right? Call it g of t. Well, that's going to be f of t minus f of 2 over t minus 2. Working that out, we're going to have 4t squared minus 4 times 2 squared, right, over t minus 2. Simplifying, we're going to get 4 t squared minus 4 over t minus 2, okay? And intuitively, right, the closer to t we get, the better approximation it should be, right? Because the interval over which we're doing the average speed is getting smaller and smaller and smaller, okay? And the other thing you might be thinking is, okay, well, if this is our average speed between, times 2 and time t, why not let t equal 2, right? Well, this is why, right? It's outside of our domain, so we can't necessarily do that. We're going to break our function. But this is where something like a calculator comes in handy, okay? Now, you won't need a calculator for this class. The calculation that I'm asking you to do right now, I'm not going to, ask you to do some sort of nitty-gritty calculation like this. I took these to a calculator for you. We can form a little table of values, right? We can look at t, right? And we can look at g of t, right? Where again, g of t is encoding our average speed or average velocity, if you prefer, on these intervals, right? So let's look at 2.5, right? Get a little bit closer. Well, g of t is going to return 18. Okay. What about 2.1? What about 2.1? Well, in this case, g of t is going to return 16.4. Let's get a little bit closer. How about 2.01? Well, it's going to return 16.04. Let's add another 0, right? Now we get 16.004, right? And this continues, right? On and on and on. So it looks like, right? This is what it looks like. As t approaches 2 from the right, g of t is approaching 16, right? Where it's coming from the right, because if you imagine a number line, right? We have 2 right here. Well, first we plugged in this guy. Let's say we plugged in that one, and then we plugged in that one, and we're kind of, coming in from the right this way. And g of t seems to be approaching 16. That's great news, right? Well, we should check that it approaches from that way from the left as well. Okay, so we'll form another table of t and g of t. Let's go 1.5. We get 14. Let's go 1.9. We get 15.6. Let's go 1.99. We get 15.96. And I'm sure you can see where this pattern is going. 1.999, it's 15.996. If you really want to go for it, grab 4 nines, right? 1.9999. That was too many nines. 4 nines, we get 9996, right? And so it would seem like it looks like that as t approaches 2 from the right and the left, g of t is approaching 16. Okay. In this case, right, this is exactly what a limit is, right? When you have this guy, right, when you have this situation right here, we can write it this way. The limit, right, as t approaches 2 of g of t, right? Spelling that out, that's the limit as t approaches 2 of 4t squared minus 4 over t minus 2. It equals 16, right? And this is even backed up by the graph, right? If you took some time to graph this function, you'd see somebody like this. We have a little hole right here at t equals 2, where you have, say 1 here, 2 here. This is going to be 8, 12, and 16. Okay, so this is what we're looking at here. We're getting really, really close to this, right? It seems to be, in a sense, approaching the value where this hole is. Okay, and this allows us to give what is admittedly an informal definition of a limit. Okay. This is informal. And the definition goes like this, okay? The function f has limit L as x approaches some point A. Written, the limit as x approaches A of f of x equals L. So it's written like that. This is true if the value of f of x can be made sufficiently close to the number L by taking x sufficiently close to the number A. Okay, where x does not equal A, it's just sufficiently close. Okay, and it's these, made sufficiently close that is the reason that this definition is informal. In a class like 221, we don't need the full formal definition of a limit. It would just sort of get in our way as far as what our goals are in this class. If you are super curious, drop by office hours and I can go over it with you. But like I said, we definitely won't need that in this course. Okay. Let's do a couple of examples. Okay, we'll do 2 of them, and then we'll get into some properties of limits that I'm sure will be entirely unsurprising. Okay, so let's take a look at one of our favorite functions, the cubic. Okay, so our question is, what is the limit as x goes to 2 of f of x? Okay, so what you need to remember here is that our limits are not asking what the function equals, it's asking what the function approaches, right? That's what's going on back here, right? This function doesn't equal anything at 2, but it is approaching 16 as I approach 2 from the left, like this, or from the right, like that, okay? So then what does f of x approach as x approaches 2? Well, the easiest way to get a hang of this at first is to look at the graph, right? Our graph is going to look like this, right? And we'll say, maybe 1 is right there. Maybe we'll say 2 is right there, okay? And cubing it, we do know that at 2, f of x equals 8. And as we approach 2, well, it's approaching 8. And as if we approach 2, it's approaching 8. So I feel reasonably comfortable, right, saying that the limit as x approaches 2, just write f of x as x cubed, that's 8, okay? But let's consider something a little bit more involved. Let's say g of x is the following piecewise function. It's x plus 2 if x does not equal 1, and it's 1 if x equals 1, okay? And of course, our natural question is, what is the limit as x goes to 1 of g of x, okay? Taking a look at a picture, what have we got here? Well, we're doing x plus 2. When we're doing x plus 2, we have a hole at 1, and we're going to do something like that. Okay, and then at 1, we don't actually have a hole. We have a hole in this subdomain. At x equals 1, our output is 1. Well, we saw in this last one that we have a well-behaved function, so we can just plug in the point, right? But let's actually look at what's happening on our graph, right? As we're approaching here, we suddenly jump down here. But this isn't the value that we're approaching. We're approaching whatever this hole is. Likewise, when we look this way, we're approaching whatever this hole is, okay? And that would tell me that our limit, as long as we can get sufficiently close to this hole, as long as we get sufficiently close that way. So that would tell me that our limit is 3, right? Because that's the value that we seem to approach as we sort of walk closer and closer to 1, okay? 2 more that I'm just going to draw pictures of. Because we don't need the actual functions themselves written analytically to get the idea of what's going on. Let's say we have 2 of these. We have this guy, right? And then we have something like this, okay? Both of these are functions. And what are their limits as x goes to 0? Well, going this way here, right, starting from the left with this guy, it seems to be approaching, now I guess we need some labels. Maybe this is 1 and -1. We're approaching 1 here. We're approaching -1 there. And 1 does not equal -1, so this limit does not exist. Likewise here, as we approach from the right, we're zooming off to infinity. And here, as we approach from the right, we're zooming off to infinity. And infinity is not a number, right? So our limit does not exist. So we've looked at sort of understanding these limits, by looking at graphs, but we would like some sort of algebraic way to do it, right? If we know that, for these base functions, right, these x squareds, right, these are all going to have these same property, right, this nice property. So if we know for these nice, functions here, we can, just take the value of it, right? We're not dealing with anything like this or like this or like this. We want some sort of algebraic properties to utilize what we just developed earlier of building functions out of other functions. We want to seek something similar with limits so we can mix them together. And I sort of did like a cooking show thing where I pre-wrote this page because and I would encourage you to pause this, write it down. But the short of it is, limits behave as you would expect. If we know, 2 functions have defined limits at some point A, right? Well, if we put one of them to a constant power like this, well, then we just take its limit and we put it to some, positive constant power, right? Negatives don't necessarily work right here for a variety of reasons, okay? If we're, multiplying our whole function by a constant, well, that constant sort of factors out, right? And we get, that constant times our limit for any real number constant. If we're taking 2 functions and we're adding them, well, we can split the limit across that addition, turn it into the limit of f of x plus the limit of g of x, right? Which is just going to give us L plus m. The same thing holds for subtraction. Multiplying functions together, same sort of thing. This limit will break over products, okay? And division is just a fancy case of multiplication. So provided that your function is non-zero, your g of x has non-zero limit, you can absolutely divide them, okay? But as I said, the long and short of these 5 properties, which are very important and we'll use a lot, is that limits behave as you would expect, with respect to their algebra, okay? So let's run a couple of examples of these now that we can calculate them this way. Let's say start with the limit as x goes to 1, 5x to the 4th minus 2. Okay. Well, we can break this up, right? We can break this up into 5 times the limit as x goes to 1 of x to the 4th minus the limit as x goes to 1 of 2, right? Well, what are we going to get? Well, the limit as x goes to 1 of x to the 4th is one of these really nicely behaved functions, right? So this is just going to be 1 to the 4th, right? So we're going to get 5 times 1. What's happening here? Well, for all x values, we're going to get 2. So the limit as x goes to 1 of the constant 2, well, that's just the constant 2 for our final answer of 3. Okay? What about this? Right? What if we have, say, the limit as x goes to 3, say 2x cubed times the square root of x squared plus 7, right? What's going on here? Well, we can break this up into products, right? We can have the limit as x goes to 3, say 2x cubed. 2x cubed is one of those nice functions. As x goes to 3, I can write the square root as x squared plus 7 to the 1/2, okay? And now look at this, right? We have the product of 2 nice functions, 2x cubed and x squared plus 7, where one of them has this guy, right? So we can evaluate them sort of one at a time, right? This is one of our nice functions, so we can just, plug our value into it. So this part is going to be, well, 3 cubed is 27, times 2 is going to be 54, okay? As before, this guy is one of our nice functions. This is just a parabola shifted up 7 units, so we can just plug in our 3. 3 squared is 9, plus 7 is 16. We then need to take the square root of that to get 4, okay? And so our limit is now just the product of 25 and 4, or 216, right? That's the power of these algebraic limit laws, okay? Let's do one more. Let's take the limit as x goes to 2 of, say, 2x squared plus 1 over x plus 1, right? And this is, we're dividing 2 guys here, right? So we can take the limit of them individually, provided that, they're both defined, right? The limit as x goes to 2 of x plus 1 and 2x squared plus 1, okay? Well, once again, both of these are 2 of our nice functions, right? We have a parabola and a line, right? So we can evaluate them as you would expect. 2 times 2 squared is going to be 8, plus 1 is 9 over 3, or once again, 3, okay? And so we've got these, right? And here's the next question is like, well, what else can we do, right? That 5th property only holds if the denominator is not 0, right? If the denominator equals 0, and the numerator does not, right? Well, then our limit doesn't exist, right? That's something like this situation. This here, this is the graph of f of x equals 1 over x squared, right? The limit here, right, if you try and divide these, you're going to get 0 as x approaches 0. Our denominator equals 0. Our numerator does not, right? So we get a does not exist situation. But what if they both equal 0, right? What if we have a situation going back as t goes to 2, t squared minus 2 over t, or t squared minus 4 over t minus 2. And you can try to plug t into this, no problem. But what do we get? Well, we get 4 times 2 squared minus 4 over 2 minus 2. We get 0 over 0. And this is something that we call an indeterminate form. Okay. And an indeterminate form tells us, well, that we can't determine anything, right? If we got 0 over 5, we would know the answer was 0. If we got 20 over 0, right, we would know that our limit didn't exist. But in this case, we just get 0 over 0. And there's two main ways that we can deal with this, okay? And the first one is maybe something that you thought of as soon as you looked at this, or rather this guy, and that's factoring, right? If we have the limit as t goes to 2, right? Well, this is t minus 2 times t plus 2, right? It's a perfect square, all over t minus 2. And that's just a 1, right? So we're, in a sense, looking at, as t goes to 2, of 4 times t plus 2. And Lucas, you're saying right away, that's awesome. This is one of our nice functions. We can just plug it in. But not quite, right? Because this is not g of x, right? Because g of x has a domain restriction, right? Once we cancel like this, we have to remember that t minus 2 is still not in our domain. But what if we called this a new function, right? After sort of this cancellation, we have this. We have g of x is 4 times t plus 2 if x does not equal 2. And it's undefined if x equals 2, okay? But what if we say, let's say f of x is 4 times x plus 2, right? They agree everywhere but a single point, right? And since they agree everywhere but that single point, they must have the same limit there because they agree everywhere else, right? So, yes, we can technically just plug t in this situation. But we do have to be careful sometimes before we just, boldly charge ahead, because we do need to consider our domain. But since we made this sort of argument here, we have analytically, right, that in this case we can plug in our t, right? Because remember, our limit doesn't care about the value at specific points, it cares about the behavior, okay? So we can plug in directly 4 times 2 plus 2 for 16, okay? Here's the other situation that we can find ourselves in, and this is our last one for the day, and I suppose for the week as well. What about this guy? Let's take a look at the limit, okay, of 1, or of the square root of 1 plus h minus 1 over h. If this looks familiar, she's from lecture 1. Okay, so what happens if we just plug in h equals 0 here, right? Let's just try that. Okay, well, we're going to get 1, the square root of 1 plus 0 minus 1 over 0. 1 minus 1 is 0, and we're in an indeterminate form. But there's this other method by multiplying by the conjugate, right? And when we multiply by the conjugate, in the last lecture, right, we already multiplied by the conjugate to simplify this, right? So I guess we'll just draw a little squiggly arrow. We'll say like from last lecture. And we get what? We're going to get the limit as h goes to 0. From that last lecture, we saw that this gets simplified to 1 over the square root of 1 plus h plus 1, right? Well, now what happens if we plug in h, right? Well, if we plug in h, we're going to get 1 over, well, we get the square root of 1 plus 0 plus 1. We get 1/2, right? And this is indeed the limit, right? We've sort of trimmed away the parts of this guy that we didn't want to deal with. And we got something much simpler, something that we could just plug 0 into without any trouble. Okay, so that's going to wrap it up for the week. If I'm managing my time well, your homework should already be posted by the time you're hearing this. If I'm not managing my time well, it should be up shortly. Okay, I will see you guys next week.